Okay. Well, we're looking at incremental language development, and our big topic is combinators. 2020 is the centenary of the invention of combinators, and let's see. Well, let's talk about what we can do with combinators. Roman, do you want to?
Yes, I mean, this is a quick overview over what kind of animals we need if we want to support combinators. I mean, it's really simple because there's a single operation, the binary combinatorial application, and then there are these constants, these combinators, S and K, and some others that are useful if you want to convert lambda expressions into combinators. And so to really support it, we need a symbol for the operator, and we need a notation, so we need an operator character. Here I use the left T because it has the correct association, so it should pass just like the left T, but obviously left T is no good in this context.
So the main issue is it's function application with different associativity than normal function application. Is that correct?
Well, I mean, it's just customary to write it left associative so that you don't need all these parentheses, but it's always binary. And there is no distinction between functions and arguments, so everything can be applied to everything.
So let me just understand what you mean by that. So I mean, for us, if we write f of g of x, it's that.
Yes.
Okay. What is the corresponding thing for combinators? If I write s of k of whatever.
Well, here you would write f applied to parentheses. I mean,
when somebody writes SSK paren SK SS or something like that,
yes. So
what do they mean?
The non-parenthesized always group to the left.
Okay, so in particular, that means, what does that mean? So if I type, if I say FGH, what does that mean?
That means F applied to G and that applied to H.
Okay. Okay. So it's like it's an infix form of what is otherwise a match fix function application thing. That's a bad way to say it. I mean, it's what it is it's a so if I look at f at star g, the whole thing, that whole thing, well, actually, let me do another one, at star h, the whole thing of x, that's still the wrong way around.
Yes, yes. It's not function composition, it's application.
I think this is a bit like having our construct, but without letting it evaluate.
In what sense without letting it evaluate? I mean,
in the sense that if we have, it will convert into f of x. So if we just let this thing be there, construct f of x, it would be a bit of.
I don't think you're right about this. I mean, I think this is a, okay, this is a taking currying seriously story. It seems to me.
Yeah, I mean, there's no notion of multiple arguments.
So right, but I think in Roman's formalism, he doesn't want to go all the way to f of g. It will stay as t.
Is that true, Roman?
I mean, combinators, when you take an expression, a lambda expression, and convert it in combinatory form, it's always in a form that doesn't trigger any valuations, right? So like kx would be an example, but only when you apply the y would it actually trigger something, and s, if it has less than 3 arguments, then it doesn't do anything.
And unfortunately, many combinator expressions have no fixed point.
Yes, I mean that's one of the main problems. So we cannot simply have global rules for the three cases that are listed here on the left, because in all but trivial cases, these would lead to infinite recursion. So if we want to actually work with combinators, we also need a way to control the order of evaluation. So,
which aspect of the order of evaluation? I mean,
because sometimes, I mean, if you have a big combinatory term, then there are two natural ways of trying to reduce this. One is to go depth first, so you go which is called leftmost, innermost, and the other one is to work on the outermost reducible terms, which may have the side effect that some of the inner ones, which don't have a fixed point, are never used and just go away. So it's sometimes a way to evaluate
look,
terms.
here's a picture. Here's a picture. These are combinator expressions being evaluated.
So which order do you use here? Or doesn't it matter in these cases?
No, applied in Mathematica/dot order.
And that means,
is
it defined?
Yes, it's defined. Strangely, this has all come up in the physics project in a big way. This whole question of order evaluation. And arguably, we should have a more global solution to that whole question. Because in the case of replace, okay, if I say, look, the sequence replace, well, actually, the new function, subset replace, has this issue in a big way, right? Because if I say subset replace, oh, great. Why isn't that working? That should be working. That's a problem. Devin, can you flag that? Because that should be...
Yes, yeah, I'll screenshot it.
Well, something
like
is
a
screwed here.
loading problem for some pack letters.
Yeah.
Yeah, that's strange.
Well, anyway, but you understand that that's going to be affected by the order, right?
Yes. I mean, the general case, I mean, it's not so much the order, but whether you go inside first or you work on the whole expression before you work on the parts.
That's one of the issues.
Yes.
This is a different issue. I mean, this is a different thing from, this is, yeah, I mean, you're talking about function evaluation. This is talking about sequence replacement, which is related but not quite the same. Okay. You do know that in SMP, I had this function, this thing that controlled the different leftmost, innermost, et cetera, function evaluation things. It's like, this is a story like the association story, which I had a mechanism that was like associations in SMP, and it didn't work out well. And so for 25 years, I avoided those. So now, similarly, I had a mechanism for controlling evaluation that didn't work out well. And so we still don't have such a mechanism. What's that?
So is that something that we should now reconsider and add to the system?
Probably. I mean, I can show you what it did in SMP. Should we look? Let me see if I can find it. I mean, I don't know what systems have that kind of control. Do you know any place where that kind of control exists? I mean, most systems, like, we have a very definite evaluation order, and let's see. This was a thing. Oh God, this was such a frigging disaster. This was the analog. Yeah, this was the association related to the association disaster. An NP is the analog of sequence. And it has the same exact disasters as our sequence has. It had an appropriate obscure name, a null projection. Okay, where is the evaluation semantics? Patterns. That was a bad idea. That was a pure function play. Oh, that was an even worse idea. That was module variables.
I like the name.
yes, that's. But the name already tells you the creature is by the way, somebody should answer the question on the live stream about where do I send a new feature request for the live stream for tomorrow. I don't know the answer to that, but somebody should give an answer. I think it works through the pre-release system, but Devin, maybe you know the answer and can give one.
I do not know the answer.
Okay, well let's get from that person. Let's get some contact information, and we'll make sure that they can send it to this live stream now, and we'll make sure it gets passed to the right people. This is cool. We don't have a procedure for this yet. Where is this mechanism? Oh gosh, this was another disaster. We should look through here for all the disasters. This was the syntax modification thing that I've referred to a bunch of times.
Macros? Or?
Yeah, it's macros.
Yeah, we had aliases right early in.
Yeah, we did. We gave them up. Same reason that this didn't work. The fundamental operations. Okay, automatic simplification. That seems relevant. Okay, here we go. Okay. This is the whole story. Each filter argument is simplified in turn unless the value k of any corresponding simp property carried by the projector, otherwise the head, is 0. This used 0 for Boolean false. Future parallel, my gosh. Okay, that's an amusing thing to have written in 1980. Future parallel processing implementations may not respect this ordering. We still don't have that, even now, 40 years later. Okay, until any projectors not carrying the property rec have appeared recursively at most k times. Okay, so do you understand what this is saying?
Okay. So we in Wolfram language, I mean the semantic, the evaluation order is always arguments before the whole function, right?
That is correct.
So this is a way to turn this around.
Yes, that is correct.
Okay.
Yes. So maybe there's an example here. We didn't yet have the notebook idea of interspersing. This is completely obscure. Oh, here we go. Here we go. May involve further projections from the same projector recursion. Unless a projector carries the rec property, it may appear recursively at most k times in the simplification blah, blah, blah. The fact that 40 years later we still don't understand this is a super bad sign. Oh, that's interesting. The SMP properties of projectors such as mult, times, and plus have value 1. Some simplifications of their projections are valid regardless of the state of simplification of their filters. which is saying basically that thing minus thing is always equal to 0, whether or not thing has been evaluated. In other words, if the hold of thing, if those are two identical holds, assuming no side effects, it's going to assume that those are actually identical and can be subtracted to 0.
And so this would be an example of outermost simplification. So
exactly,
which means that even if thing would explode, you would just
exactly,
eat it up, right? Yes.
right,
That's
exactly,
the kind of thing we need for combinators.
Right. Right. So the classic example here was doing, okay, so look, here's factorial, right? So this is an unterminated factorial, right? So that g of 10 evaluates to 0. Whereas in what we would get if we did the same thing here, right? And we typed in g of 10, kaboom, recursion limit, right? But the reason this doesn't,
yes, why
the reason this doesn't do that is because here this property, it's trying the multiplication. So it's somewhere in the sequence, right?
Oh, it multiplies by 0.
It multiplies by 0,
okay,
and then it does outermost, and then it's done.
Okay.
Okay, so this is what happens. Oh, this is tracing multiplication here.
Oh, there is the 0 times g, yes.
Right.
Yes, that seems like a useful thing to have.
Oh my God. 40 years later. Okay, let's have a little talk about this, whether we can actually do something with this. Okay, so in modern terms, that is it's a version of hold. What is it? It's a version of hold where you're doing a trial evaluation of f without evaluating what's inside.
Yes.
So for us, yeah, Bob on our live stream is saying it's like a game of chess. You try simplifying in all possible ways until you find a winning simplification. Actually, let's think about that comment in the light of 40 years worth of additional information like theorem proving, for example.
Yeah, I mean, it's just like trying several strategies and see whether one of them gives you.
No, but this is a different thing because it is correct that the issue is it's like given a set of rewrite rules, does there exist a sequence of rewrite rules that gets to that doesn't loop forever, basically, that terminates, right?
Yes. Now the problem is that in many cases, when there are infinite reductions, then the finite ones are not unique. So you may have more than one that terminates to different results.
Well, okay, so let's think about that. So in the case of if the thing is confluent, that will, well, yeah, then the game is over.
If everyone terminates, then there's a unique result, yes.
In the case of confluence.
Yes.
Right, but in the case of confluence where not everything terminates, what happens then?
It's a long time ago since I worked on this. So the question is under which conditions do you still have unique finite terms, even if some chains are infinite?
Right.
That I don't know.
bizarrely, this has come up. This comes up. A version of that question comes up in the physics project.
I mean, it is inherent to many kinds of simplifications and rewriting, right? I mean, it's no surprise that it comes up in such systems.
Yeah.
And I mean, the way I understood what you're doing is you have big system and you go in and different places and make changes to different parts. And so this is very relevant, this question of termination and uniqueness.
Yes. But the issue here, okay, so the question is, if, okay, one result would be that, okay, can you find a finite answer? So this is also relevant for replace repeated, right? Replace repeated has a very dumb strategy right now for trying to get to a fixed point, right? I mean, the question is, can you get to a fixed point, and is there a unique fixed point? And do you care if there's a unique fixed point, or do you just want some fixed point? Right? So, I mean, okay, so in the case of, okay, so, for example, okay, so we have replace repeated. What other operations? I mean, in principle, also mainstream evaluation is another example of something which, evaluation and also find equational proof, I claim, question mark. And the big issue is, does there exist a path that terminates? Right?
Yes.
And now
and if there is there one strategy that will find it?
Well, I remember a result when I worked on SMP 40 years ago. There was a claim in the recursive function literature at that time about some kind of outermost strategy guaranteeing to work if it was ever going to work. If anything was going to work, it's going to work.
Yes, I dimly remember something like that too. So it's clearly that outermost, which we do not use, which is more likely to find.
Look, outermost is basically lazy.
Yes.
Right.
Is there a way to support this for replace repeated and evaluation that doesn't cause the headaches you had 40 years ago?
Well, look, the number one headache 40 years ago was nobody understood nobody understood this at all. Okay, I mean, this was just utterly obscure. And let me just save this in the right place. And then I want to loop back to combinators and what will be useful for them. But I think we are actually onto a more general issue of evaluation here. So, okay, so the question is, let's take the replace repeated example. Okay. So let's have a real example. I think I had one recently that was just not very clear whether there was a path to termination. Well, let's say you're doing the 3x plus 1 problem as a replace repeated. Right? I assume you can do that. I mean, if I write something which says if even q, well, I could do actually fixed point is another much more obvious thing.
Yes. The 3x plus 1 problem doesn't suffer from.
No, it doesn't suffer from these kinds of issues.
Just that you don't know whether it terminates.
Okay, but so let's take fixed point as an example. Or is that an easier one as well? Because it's just going f of f of f of f of f. I think that may be easier because it doesn't have multiple functions involved.
Yes. I mean, you do not start with some big term that may explode, but you build it up from the inside. So I think it's more harmless.
Right, but replace repeated could go wrong, because replace repeated, I could be doing. I mean, I literally wrote something let me show you something I just wrote recently for some real purpose. Okay, here we go. So what this is an attempt to build a Cayley graph from relations. Okay. So let's run it and we can see what it's doing.
So relations as in group theory?
For example, yes, but not
Okay.
necessarily group theory. But so this is a free group. This is the Cayley graph of a free group. Okay, so now I add the relation AB goes to BA. Okay, and then this closes its arms up. And so this was an attempt, that's an actual group. And that was maybe, that's a cyclic group, I think. Maybe Jose can recognize these things.
Yes, it seems to have two generators of order 4 and 6.
So this was an attempt to do the quaternion group. Okay, so I have a function here, reduce word. Okay, so that's doing a string replace list. It's attempting to do a fixed point to reduce a word, but we know that, I mean, this is the word problem for sort of semi groups, or in one special case, it's the word problem for groups, which we know is undecidable. So this is a quintessential example of something that might not terminate, and it depends on the order in which you do these replacements, if I'm making sense, right? You can, this is trying to generate all possible replacements, I think. And yeah, I mean, this is a typical theorem proving type thing. It's generating all possible replacements and trying to find whether any of them,
Yes, I mean that's one thing that theorem provers they control the order of evaluations to avoid
exactly
branches that do not
exactly. I mean, that's the, and by the way, a comment from Bob on our live stream: could neural nets guess the next best simplification? Yes, the answer is yes. That's an interesting thing that we've been experimenting with in strategies for theorem proving and so on. And actually, we probably should do more with Simplify on that. I think we've done some little stuff with that, but there's probably more that could be done there. Anyway, okay. All right, so let's come back to this for a minute.
So we would need something like in replace repeated and also in the evaluator that controlled. That is, I mean, main would be outermost and innermost, right? Those are the two most important ones.
Okay, well, let's think about what that would look like. So replace repeated.
I think we could parameterize this by taking Romance expressions with left t and deciding in which order we replace each left t by construct. So if you go to the left notebook,
yeah,
and take that expression with left t's and replace, just do replace of left t goes to construct.
In here?
Yes. Right, so we get these different things, and if A, B, and C had down values, then they would evaluate.
Yes.
So I think the question is in which order this replacement is working.
Or sub-values, by the way, notice.
Yes, exactly.
Right. I see. So the question here is, does it try to evaluate the unresolved, I mean, the thing which is still, So you're saying it's a function application, but it hasn't yet been turned into a genuine function application.
Yes, I mean the input you're using here is just to illustrate the associativity properties of left t. So the first and second term are actually are actually the same. You see, because in the input I use those
No, I saw that you
parentheses,
parenthesized.
which just to show that the parentheses on the left are not necessary, but on the right they are.
But I think the advantage of Romance notation is that even if A and B and C have down values, they will not fire.
Yes.
If we try to use this notation, we would have to be holding everything continuously.
Now, unless, of course, we would, if we were to implement global rules for S and K, then, of course, we would run into the same problem that we couldn't control how it evaluates. And so my proposal is essentially to not have any global rules for S and K, but just have
to
a
have a
notation
combinator evaluate or something.
and then have functions for, say, evaluate outermost, evaluate innermost. Now, of course, if we are going to do that for general replacement, then we should use the same machinery for both cases.
Well, I mean, one way to do that would be to say you're not doing actual function application. If you want, in other words, imagine that there was a version. So normally we have f of x, right? But imagine that we had f, left t of x is function application. It just is function application that never, that only uses own values.
This is essentially, this is what combinators do, right? Or what this symbolic application operation does. I mean, it just sits there and waits for rules to be applied, and the rules would not be globally defined.
So essentially, this is a symbolic. I mean, it's otherwise okay. So what's the analogy between this and inactive heads?
I mean, it would behave the same way, but it's just that using square brackets in combinators would just makes terms unreadable.
No, I understand that. I understand. Let's not worry about the syntax for a second there. I'm trying to understand the semantics of evaluation here. And what you're saying is, if the combinators were fundamentally inactive, then what you're describing is an activation strategy, right? In other words, if I had something which was, inactive, let's call them, well, let's say inactive of f of inactive. Am I about to get this the wrong way around?
I think I agree with this idea that this is what's happening. In which order we inactivate things.
Or de-inactivate. Which
de-inactivate.
order we activate them?
Activate, sorry, yes. In which order we activate.
Oh, wow. Look at that. Why didn't they typeset?
Well, because they don't have an argument, probably.
Exactly. They are not heads.
I see. They could typeset, but okay. So then the idea is you've got a whole nest of inactive things, and you try to have a strategy for activating. And we could even imagine using the theorem prover, given that we know these combinator reductions, right? We could imagine using the theorem prover. So I think our existing theorem prover should work for this case, shouldn't it? I think so.
I think so, yeah.
I think that's just one of the, I mean, it's just one of the things that, so, I mean, okay, so a very minor thing we should do is get combinatory logic into the theorem prover as an axiomatic system. So that's a good question. If we look at axiomatic theory, right? If we say something like, I don't know, the Scheffer axioms or something. So here, we do have essentially this idea. That is, we have well, in these cases, these are more algebraic, and so they tend to have dot operations, not function application. But combinatory logic is basically something where, I mean, we could as well use dot, except for certain issues of associativity, right?
Yes, I mean the combinator logic has just that single combinator application operation.
Okay, so the first most elementary thing is get the combinator axioms get the original Schoenfinkel combinator axioms into axiomatic theory, because then the theorem prover.
Well, that's an interesting idea.
The theorem prover should be able to give us, well, what will it give us? It will tell us, does the theorem prover have the capability to find a reduction? It knows, given, is this equal to this? It could do that. Do you think there's a way of using the predicate logic theorem prover to determine whether the thing is terminating? What is that? What kind of a logic question is termination? I think it's probably undecidable, unfortunately.
Yeah, but that sounds like something that somebody has already thought about a long time ago. I think somewhere.
Possibly nearly 100 years ago, right? More than 40. Go ahead.
I'm thinking that what we can encode in the prover is a set of relations.
Yes.
It's some sort of particular strategy, not so much the general evaluation. Because what could be an action for evaluation?
Well, one of these, right? I mean, this is what we would encode. It's just that it's just axioms, just like these ones. It's that S of X, Y, Z is equal to this.
Right. So it's a particular case, not the general case. You need to specify what your combinators are.
Yeah, you need to have combinator symbols.
Yeah.
Right. It is a specific combinatory logic. Okay. So now the question would be, okay, so for example, okay, let me just think for a second. So then the idea would be, that's one thing, is to get the pure, I mean, this is the difference between equations and evaluation, right? In other words, the statement, X double equals 7 or something is a different statement from X equals 7. This is a bunch of relations. I mean, so we can treat S of, K of X and Y as reducing to X, or we can treat it as being equivalent to X, if you see what I mean.
Yes. Now with combinators, we clearly need reduction because we don't want to go the other way.
Well, maybe. I mean, I guess so. I guess it's a one-way. So I guess the difference is that it is like theorem proving, but it's like these things I've called multi-way systems, which is like one-way equations. So it's a semi group.
But in general, there are proofs in which we will need to expand X to KXY as an intermediate step. So it's not always
true.
I think so. So I don't think it's always true that we need to reduce. Sometimes we need to expand temporarily and then reduce.
If we're trying to do a proof.
Exactly. Yeah. And I think the prover.
Well, it may also be the case that even in a reduction, even in something we think as a combinator reduction, that the efficient way to do the reduction is through a proof, that there exists a way of getting there by going K always reduces out, but it is more efficient to allow it to go the other way, potentially.
So I think with the prover, we cannot ask what's the final reduction. It's more like, is this reducible to this other thing? And then it would try to find a path.
Indeed. But I mean, so the question is the kind of the search of what is the reduction. In other words, this is, what we're trying to do is combinator simplify. I mean, that's the ultimate function that we want. We're not going to have, combinator. It's more like simplify. It's not like evaluate, I claim. Because evaluate, in our normal down value sense of evaluation, we would get rid of all the K's and S's. We would reduce them out, but that's not going to be possible here. Right? All we can do is say, what's the simplest combinator expression equivalent to this, which potentially could be a combinator expression that doesn't terminate. So combinator simplify could go, you feed it a non-terminating expression, and it returns a simpler
Normally, non-terminating ones don't get simpler, but
What do you mean? I mean, you can certainly have.
They usually explode, right? I mean,
Well, I don't think that's the case. I think there are ones here. So I think I have examples. So look at these. Look at these things. Okay. So these are. So here's an example of one where it gets up to 5,000, and then it cycles.
okay.
You might think that you enter one of these large ones, and it should be able to find the original one, which is simpler.
Boy, oh boy, oh boy. So that is not combinator reduction in the sense of that's exactly right. I mean, that's a thing where, so I mean, look at what's happening in these cases. What's happening in these cases that's really kind of horrifying is the cyclic behavior. Now, remember, this is a particular evaluation rule. See what I'm saying?
And so the slash dot tool is innermost, right?
Let's figure that out. Okay.
Because it evaluates all the parts, right?
Okay, this was the rules. The heck is that? Oh, that's compilation of a lambda expression. And that's church numerals.
Yes.
Okay, so what we've got there, okay, so those are the combinator rules. And now we could do an actual combinator reduction for plus. Okay, so there's the increment operation. Okay, so what we should get, there's the 0. Okay, so increment of 0, right, is that. Okay, so the claim would be, actually, okay, let's do the extreme case. Let's do a times. Let's do increment of 0. Okay, so that should be the church numeral for 2. And let's do, if I'm not mistaken, the times of, and it's curried, right? So it will be the times of the increment of the increment. Is that right?
Should be, yes.
Okay, so let's see what that reduces to. Okay, so now we've got C rules here. And now in principle, what we say is, well, let's do a,
I mean, here it wouldn't matter, right? Because it terminates, so.
Well, let's find that out. Okay, so // dot C rules. It's the same frigging thing. How can that be? Well, let's find out what, oh, look. Nest increment 0 4 times.
No, that's different.
Okay. Oh my gosh. The nest of sk comma n can be converted to the church numeral for n by applying this thing here. Okay. Well, I don't understand why that's different, and I don't understand why that didn't reduce. And it may be something to do with the way /dot operates. Let's see whether increment, go ahead.
Perhaps you need to apply C rules as well to the nest result.
Something's wrong here. Power. I just didn't know that you could get, okay, hold on. I was supposed to integer n.
No, I think the problem is that these numbers are still function operators. So you have to apply it to something.
Oh, yes, you're right. I guess you're right.
And the number n is n-fold application, so you have to apply it to two arguments, to an f and to an x. And then you should get 4 f's applied to x.
Okay, so let's try %270, which is increment 0, right? So you claim that applied to an f and a g, you think?
Yes.
Okay, so now this,
Oh, yes. Okay.
brilliant. Okay, so then this here, after multiplication, right? Applying that to, why do we need to apply it to both f and g? Why isn't it just to f?
Well, the result of applying to f represents n-fold.
I see.
N-fold application of f, and to see it, you have to apply it to an argument. Okay, here we are.
Brilliant. Okay, so this thing here, yeah, that's what all that prattling about nest was about. Okay, so this is an example where it terminates, right?
Yes.
Okay, so now elsewhere I discuss let's see. Another one of those terrific pages of code. That's a universal.
I mean, there's no way to typeset these nested things, right? I mean, there's no reasonable way to do it.
Well, I mean, we don't know because they haven't really been done for years, so we don't actually know. It could very well be. Okay, where do I have this stuff about combinators? Hold on.
But presumably using your left T, this would look nicer.
Yes. Okay, there's the combinator thing. Combinator properties. Okay, here we go. Okay. At size 7, all but 2 of the 16,000 possible combinator expressions evolved to fixed points. Okay, so here's an example of a combinator expression that doesn't. Okay, so now if we go nest list /.crules. Okay, this is our first example of a non-terminating rule application in this way of doing it. Okay, and with very obscure output. Right, so if we go here, I don't even know what we compute here. We could compute leaf count here. So if we say leaf count, even that sequence is just something totally bizarre. Okay, I'm now curious. If we go a bit further here, let's go to 20. That may be living too dangerously. Let's just see what happens to the leaf count there. Okay. See in modern times whether we can tell what this is. Not a good sign. If it doesn't come back immediately, it's usually not going to come back. Okay, but so this is a good example. This is an example of a non-terminating combinator expression, right? Under combinatory reduction, supposedly. Okay. I don't think it's finding it, which is even bizarre in its own right. Into expressions that grow like 2 to the t over 2. Well, let's find out whether they are linear recurrences. Nope, they're not. Okay, well, that's totally weird. Okay, so let's ask whether there is a strategy for evaluation which would cause this to, I mean, maybe this simply doesn't terminate, right?
Yes, I mean, it's possible that it doesn't matter which order you apply to.
But termination might be. It could be if I take one of the other terms here. Let's say I take the one from here. Then it is the case that there is a combinator simplification because that guy. Oh, by the way, I want to see what this looks like if we implement it with left T. So that guy is in fact equivalent to the simpler combinator expression, right? Okay, let's see what this would look like if we used left t for it. How would we do that?
With a pattern, A blank bracket B blank goes to left t. Arrow left t AB.
Okay.
Left t.
Left t. AB. Okay. All right. Now I take this expression here, and what do? I just say / dot that.
Yeah, I think so.
Certainly got no lack of parentheses. I mean, that's moderately ugly. I mean, I don't know which is more obscure to read than which. That one has the advantage that you know what function is applied to what function. I mean, this is just, you know. I mean, by the way, you know, combinators in real life, my examples here are some of the better examples of combinators in real life. I don't think you find, you know, people haven't done computerized combinator stuff much. So I'm not buying this. I mean, for very small things, I can see that this might work, but for something from the wild, this doesn't seem to be a big advantage.
Well, but I find the lefty form much easier to read.
This form? Well, okay, fine. I don't find either form very easy to read. Let's see what this would look like, just for fun. Oh gosh, it's all in the head, right?
Try with the lefty.
Let's try that. Definitely better. I mean, that's better. That's a real tree.
Yes, and we see the repetition. These longer leaves.
That's a good point. How do we turn this into an ordinary tree? We don't have that yet, right?
No.
Expression tree is the thing that would turn it into a tree.
I guess it would be equivalent to the original expression. So changing left t by construct here.
What do you mean?
I mean, if we apply to this output 287, the rule before, left t goes to construct, we should recover your original expression.
Oh, sure.
Yeah. So that would be the expression equivalent to this one.
Right, but that's simply saying that this is the symbolic version of function application, right?
Right.
Which is otherwise known. We could write this as, okay, so again, repeating that. I mean, what we have is construct of AB does that. We could imagine a symbolic construct AB, which is equivalent to left t.
Right. Or an inactive construct or delayed constructor.
Right, but what's the difference in inactive construct and just inactive of the head? Because the symbols here, I see that, because inactive is, the only thing inactive does is to prevent down value evaluation, right?
You could say inactive of construct, right? I mean,
Exactly, that's what I was thinking. Because this is more symmetric. So in this language, I think everything is a function. Both A and B is a function, while for construct, A is a function, B is an argument.
Yes. So what's your point?
That treating A and B in a symmetric way, rather than inactivating A applied to B, is more natural.
Okay. All right, but so what are you going to do with all this stuff? So I mean, we've got
So I think the main point here is that we see the difference between the purely typesetting, how do you input stuff, versus what it actually semantically means.
Okay, let's zoom out for a second. We've got two issues here. One is the pretty interesting question of whether we support a different form of evaluation semantics, particularly relevant for replace repeated. And I mean, the other is specifically about combinators. And the question is, what on earth are people going to do with combinators?
So my proposal was essentially to provide the notational support for doing whatever people want to do with it. So we need that combinator apply or inactive constructor. And then we need the operator symbol, a nice escape form, and a nice output form that does what that looks the way it's supposed to look as a combinatorial expression. And then we need that T operator that turns lambda expressions into combinators, and the reverse, which turns it back into lambda expressions. And then we
but in general, wait a minute, there are specific lambda expressions that we can compile into SK combinators. But the general lambda expression that involves, you know, square roots and things, we can't compile it into SK combinators in any
I mean, we would the square root would be a constant, right? I mean, it would be.
But our list operations also, there's no way, right? I mean, the list operations are just way more complicated than combinator things.
Yes. No, I mean, lists, you would probably treat lists as projections, right? I mean, a list is a tuple, and the tuple can be represented as a combinator.
How?
Well, I mean, the tuple would have the property that when you apply probably church numerals to it, right, that it would give you the correct component. That's one way of doing it.
That's extremely obscure.
Well, yeah, I don't know whether there are better ways, but I mean, there's clearly a pair construction in combinators.
Yeah, right. Fair enough.
Even F and T falls in two. I mean, the conditional is particularly nice because the conditional just applies that a truth value is a conditional, right? The truth value applied to two arguments, x and y, gives you x if it's true and y if it's false. So the if expression is particularly nice in combinators.
Okay, look, the basic, you know, sociological fact about combinators is next year they will have been around for 100 years. They haven't exactly taken off, you know, yet as a practical thing to use. Partly because, I mean, it took probably 40 years for people. How long did it take for people to understand that combinators were equivalent to lambda calculus? It took until Curry and so on, right?
Yeah, I mean, that was very early, right?
It was, what, end of the 1930s or something?
Oh.
Well, whatever. But I mean, okay. But then, okay.
I mean, I think they were more or less developed together, right? And until somebody found out that the Y combinator destroyed everything.
In what sense?
Well, because everything has a fixed point, and so a language where true and false have fixed points is not very useful.
What do you mean?
Well, because it always gives you contradictions.
Wait a minute. I don't. This is a piece of combinator law that I do not know.
Mm-hmm.
So what you're saying is, I mean, the Y combinator gets to a fixed point.
No,
Y combinator. What's that?
Yes, I mean for every expression x, y of x is a fixed point of x, and so everything has a fixed point. So now, what is the fixed point of negation?
Well, but I don't understand. For example, that combinator expression I just gave with the s's, what would be its fixed point?
Well, in most cases you cannot actually compute them, but the point is that there is a reduction that reduces y of x to x of y of x.
I understand by the definition of y.
Yes, ultimately y is some soup of s's and k's. But
Right.
there is one reduction, but
No, but there's an equation involving y that y asserts is true. But in the case of the expression that I just gave, that doesn't terminate. What does that mean for, I mean, that's then an equation that is one of our outermost, true only in outermost form equations, I think.
Probably, yes.
Right, that is, there exists a fixed point, but that fixed point, you know, it blows up before your very eyes, so to speak, as you apply the Y Combinator. Right, depending on which order you apply the thing in, it's either, if you do the innermost application, that S expression is going to just blow up.
I mean, if you look at the derivation of y, I mean, that basically gives you a sequence of steps that goes from y of x to x of y of x.
Right, assuming that x doesn't blow up.
Yeah, assuming you never touch it, right? So
right, so that's an outermost, but
outermost, yes.
That's an outermost reduction. Right. So the idea would be, okay, so here's a general concept for function. You know, in other words, see what you can do with the outermost functions before you ever go down inside.
Yes, I mean,
I think what you have to,
very useful concept for working with combinators, and probably also in other cases.
Let's think about other cases. When would that be useful? So so see, in our evaluation semantics, there are two things going on. There is a function being reapplied, and there is continuing to walk through the expression. Those are two different types of things, right? So in other words, in the case of map, no, that's not a good example. So, you know, when you do, let's say we do
factorial example you had earlier, right? I mean, that's what.
Yes, but I mean, in general, if we say f of g of x, comma h of x, there's both the evaluation of g, which could blow up, right? But then, yeah. This is the example, right? So take a look at this, right? So what do we do here? What we do right now is we try and evaluate g of x. Okay, we try and get a fixed point of g of x. And we do that innermost. We try and get to it. Let's say we did that more outermosty. We wouldn't finish doing g of x. We'd try g of x. We'd say, oh, that's hopeless. Let's stop. Let's do h of x instead. Okay. Now, it could be the case that f is a function defined so that if its second argument is 0, the whole thing is 0. So after we've tried g of x for a while, we try h of x. Oh, h of x goes to 0. Therefore, the f is 0, and we're done. We don't care what g is.
Yes.
Right, but remember, there are two different things here. So the other thing that could happen is g of x could turn into something else. In other words, there's a chain below g of x. And then but that chain, the same thing could recursively happen in the chain below g of x, that it could have something else where there's a branch where you do the left one or the right one. Okay, let's look at what I did 40 years ago. I think I had a scheme for dealing with this. I think that's what this K thing is all about. Carries the property rec. It may appear recursively at most K times in the simplification of a filter in this thing before the simplification of the projection is performed. Okay, that's exactly this. So that's saying this thing G in the evaluation chain down here can appear at most K times before you stop and you try and you keep going and then you try and do the F. See what I'm saying? So the innermost strategy would be this property of G is infinity.
Yes.
So you go, you just keep going down that path, right? The outermost strategy would be it's 0. Don't even try to do G. But ultimately, with outermost, you won't get anywhere because in the end, to resolve F, the
Yes, I mean, an example would be 1 minus 1 times something, right? Where you would need to look at the argument to see that it is 0.
Right, times 1 minus 1 x. Right, you won't be able to resolve that without doing, and that's why. So I think the strategy that I had there is a bit coarse, but the strategy would be, I think it had some way of making progress. Let's think about this for a second. So again, let's look at this in the case of replacement. What is the analog of this for replacement? This is for evaluation, which I think will be very, very tricky to deal with. I mean, in other words, we could, okay, let's imagine that we had a wrapper called tentative evaluation, let's say. Okay. And that what happens is that tentative tries evaluating once, one
It's
level.
like having a very small dollar recursion limit or iteration limit.
That's true. So what would happen if we do, okay, let's try that. Let's try that. Let's say block dollar recursion limit equals 4. Let's define our factorial.
I think there is a minimum value.
At least 20, okay.
Not F.
Oh, not F. Why did it return that whole? Why didn't it return the whole sequence?
I think this is standard. When there is a recursion limit, it always returns a whole thing.
But look at this also. During evaluation of fac of 8 minus 1. Okay, I'm sorry. I need to try a smaller factorial here. I need to try factorial of 10. That's frigging weird. I see. It never went back up again. It never went back up again and found out that it had a 0. See what I'm saying?
Right, yeah.
Yes, because it's still innermost, right? I mean,
Right.
I mean, we need to catch this hold and do something useful with that if you want to implement that tentative thing.
But a way to think about this is, I mean, this is one-step evaluation is what we'd have to do here, right? And
yes, I mean, the recursion limit, when it's hit, then it gives up. But if we had some other way of, say, do a couple of steps and return whatever you have, then that 0 would surface.
right. I mean, if how would you define a step? Is it one element on the stack?
Yeah, one application of.
Let's see what this looks like. If I echo the stack here.
I mean, essentially what slash dot would do, right? But
hold on. What is the stack? How do I get the stack? What is it? What's the name for the stack? Is it just stack? Yeah, I think so. This may be very horrifying, what happens here. No, that's not where I want to put it. What I want to do is I want to put it in the definition of FAC here. I want to put an echo I want to say echo stack semicolon that. Let's see just how horrifying this ends up being. Okay, now let's try this. Ta-da! How did that happen? Let's try a smaller factorial here. Well, I see we have to go 20 times down. Recursion limit exceeded during evaluation of infinity? That's something very, very funky because that was a stack depth. The thing was that's
Yes,
why we set a minimum dollar recursion limit.
Because it tries to format the stack, and that runs into the same recursion limit.
Right. Exactly why it returns 0, I'm not completely sure. Well, okay. In any case, but let's go back up here. So, could you walk me through what the thing is for replace all, but replace repeated rather? What's the analog of this for replace repeated?
No, what I meant was replace single replacement. That's one step, right?
It is, yes.
Yes, and so we need a way to say whether we go inside first. Or...
Exactly. So in replace repeated, right? This is what we need. In replace repeated. Okay, let's look at this. Let's clear FAC. And now let's say FAC of x blank arrow x times FAC of x minus 1.
Colon arrow. Or does it?
Yes, colon arrow. I think that's right. So Mohammed on our live stream is talking about quotes. No, that doesn't solve the problem. That's that is a very naive and simple. Hold is a much better version of that problem. But the problem with hold, the problem of quotes and the problem of holding is what holds the holder of holding. I mean, it never works. It's just a band-aid. Okay, so let's look here. So if I say replace repeated, well, actually, let's just try the most naive thing here. Replace repeated of FAC of 5, comma this, I think we'll run into an iteration limit. But I'm wrong. How did that possibly work? Okay. Let's do this. Go ahead.
Because it evaluates before it goes to the next step, replacement, and so the 0 times happens.
Well, that's nice.
But of course, that intermixes the controlled evaluation of factorial with the uncontrolled evaluation of times. And so we would need to get hold of both of these. So instead of using times, you would
let's just see something. I'm curious about something here. So this here, right? If I do replace repeated of fib of like 5 here with this, I don't think this will do what and I say
replace repeated
/ timing. Oh, there's no end condition. Ag. Okay, that's another horrifying thing, right? Because I would be, well, let's put the end conditions in as assignments. I don't think it's going to matter to what I want to show. Okay. Now let's try fib of 10. This is very interesting. Do you see what I'm seeing? What's happening here is that this is not, innermost evaluation would have complexity phi to the n. Right? This isn't doing innermost evaluation. So if I were to do,
does it group? Does plus?
Yes, because
oh yeah, yes, of course.
it does.
Same
Plus
as the zero before, right?
Right. So how can we see that? Can we see that in how can we see that? We could see that by doing an echo somewhere here. How could we see that going on? I guess if we do, yeah, if we put an echo in here, well, at least we could echo n. I think if we echo anything else, it's going to go crazy.
But it's an interesting question. How do you see the intermediate things that get applied in replace repeated?
Yes, I understand. Help. Okay, that was not a good sign. So let's actually do something different here. Let's sew these, and then let's reap them on the outside. Okay, I don't understand this. That seems to have an awful lot of values in it. See what I'm saying? Well, let's find out how many values that has. It certainly doesn't seem to have 10,000 values, so that's a good sign. Oh, for goodness sake. That's not what I want. So I want part 2, 2, 1. Okay, let's do this. Let's do this. Let's just compute. Actually, forget the timing for a second. Yeah, there we go. Well, this is also telling us the evaluation order. So this is giving us, so that thing there, okay, that's the evaluation sequence in some sense. So I claim this is probably going to be quadratic in n. This thing, if I do this for
what happens if you use nest and single replacement or nest list? Then we should be able to see the intermediate.
Yeah, we should be able to see it. And that, I reckon, it's hard to know. Hard to know. Let's go up to 20. Let's see what it does. It's not my favorite quadratic increase. Doesn't look very quadratic to me. That is frigging weird, because that's not the golden ratio. Right? It's smaller than the golden ratio, but still exponential. All right, there's something to understand here. But your point is that if we did this with a nest, I don't know whether it's actually true, but let's try it. Okay, so let's say we have a nest list, and this is just a hash / dot that thing. Well, actually, we can just say fixed point list. I see. What's happening is this.
Yeah.
What would happen is if what we put in there was so let's say fib of let me ignore that and let's just do this fib of 10, for example. Watch this. Okay, so this is actually quite interesting. Okay, so there's the answer. Right?
Some simplification, but not complete.
Right, but look at this. If what we did was this, why the heck didn't that work? Oh, because the expand doesn't get done at the right time.
Yes.
This would work, I think. It's shorter, but not much shorter. What's that?
The expand around the whole thing.
Oh, yeah. Right. You are correct.
Okay.
Okay, but now this is yet a different, bizarre version of outermost evaluation, right? Because you have to have a helper function.
Well, I mean, it does outermost, but it also does some parts innermost, right? I mean, we took control of the fib, but we did not take control of the times and the plus.
Right. But if you do nothing innermost, nothing's going to happen.
Yes.
Right? The thing's just going to sit there lazily.
Yes. And so what started the whole thing about this tentative was so that you need some innermost steps in between. That seems very relevant.
Right. But what this is saying is, I mean, parameterizing, look, what this is basically saying is, in replace repeated, there are two things in replace repeated. One, the ability to have an intermediate function, apply an intermediate function between repeats. That's one possibility, right? E.g., expand or something.
Yes, and also for tracing, right?
Yeah.
Just like echo also.
Right. Okay. The second thing is, which part of the expression is the /dot applied to first, right? And that's relevant in the case of f of g of x, h of x, because we could apply that /dot. Is the /dot applied innermost? I don't even know. Do you know the answer to that? If I do a replace repeated, let's say I say x blank of y blank, x blank of, well, let's just do x blank of y blank goes to hello, and then I say f of g of x. I got it the wrong way around.
Probably still have some f's or g's defined. No.
I think this is more bizarre than you think, because I think if we do this, what the heck? Is G defined? Oh, I think G was defined.
Okay.
Otherwise, this is just incomprehensible. Okay, so that is going innermost, right? In other words, it didn't, well, that's going in some bizarre outermost way.
Well,
This,
does
go
it
ahead.
matter? I mean, you still have one left, whatever you do first, right?
Yes, it matters because in this intermediate simplification thing, if it was f of hello, that could evaluate to goodbye.
That would still match the rule.
No, but I understand that would, well, in that particular case, it would still match the rule, but you could imagine that it would no longer match the rule.
Now, if you do x of y colon arrow x, then you should probably see what. No, it doesn't matter. Yes. You cannot have something that matches the right answer.
Well, right, but I mean, look at this. Right, so that's the general case of what can happen, right? There's no guarantee that it will, you know. But the question is, what's the answer?
Outermost.
Right, but the question is, what should this do? And what would you even want this? I mean, in this particular case, just going to cycle forever. Let me ask another question. I've got to go in a moment here, but imagine this was being done concurrently. Imagine there were multiple parallel programs that were doing this asynchronously.
Mm-hmm.
There are only certain confluent rewriting systems where the answer, I mean, in most cases, the answer would simply be undefined. You could get a whole variety of different answers. Unless there's confluence, maybe and termination, I'm not sure. Wow, it's amazing that we've been able to go 33 years without this stuff. I mean, look, I remember when was it? I think it was actually, this happened even with SMP, because SMP was, and also Wolfram Language is an infinite evaluation system, right? And there were all these people who said such a system is impossible. It was a very common thing that I heard. When people knew that it was an infinite evaluation system, they just said, "Oh, it's impossible."
I mean, the attributes, the hold attributes, certainly. I mean, they would also probably be relevant here because they would actually prevent the innermost evaluations and still go away automatically. So I think we should also look at the hold attributes, how they play with this.
Right. Well, I'm afraid we're going to we need to wrap here. We should meet again about this. It's very interesting. It will be nice. Okay, so I have a suspicion here that if we can solve this decently of parameterizing evaluation order, that this will be useful for a lot more than just this. It'll be useful for and I also have a feeling that it will be relevant in defining, in effect, locking for concurrent processes, because I claim this is a highly related question. I claim this innermost, outermost, what gets evaluated when is closely related to, is the result ready from a parallel, from a concurrent program? Do you believe that, or do you think that's the? So in other words, this question of is it ready yet? And do I want to, like, for example, I could even say, I don't care what result that program gives, because I'm going to multiply it by 0.
Mm-hmm.
But the question of whether you try, so here's the issue. The issue is in most ways of doing concurrent programming, you have these various kinds of locks. And you say, I'm not going to go on and do any more to my code until everything came back from, by the way, talking of parallel programming, did you see this? I have my 40 cores actually up and running, and I computed something all night on all 40 cores. It took 11 hours and actually came back with an answer.
Very good.
It
Did you
saved
see my email about the new version of that dialog is now that
yeah, I know.
version
I don't want to use the prototype build.
Okay.
So
Okay.
because I've got because if I'm running the thing all night and I'm generating 7.5 gigabytes of output, I would prefer if the thing didn't crash because it's a prototype build moments before it returned a result.
Mhm.
In any case, do you get what I'm saying? The point that I'm making is normally when you think about concurrent programming, you have to say, in order to go on with the computation, I need to block until everything returns. Like, parallel table or something blocks until all the table results are there. Parallel
Yes.
try does not. Parallel try waits until something works, right?
Mm-hmm.
But actually, what is the analogy here between parallel try and, this feels like versus parallel table. Parallel try says, well, I don't know, that's quite an analogy, but my point is, if we could figure this thing out with Bob on this live stream is asking, how do I have 40 cores? If you look closely, you'll discover this is multiple machines. And that's using, they're set up as in the parallel process configuration dialog, you can hook in different remote machines. I'm hoping to have another 20 in a few days.
Mm-hmm.
And I'm also going to actually be running using, I'm going to be running a batch processing on AWS, which hopefully will work too. Anyway, but this is the thing I'm describing is a good idea. Do you get it? Does anybody else who's here? If everybody else is still, the point is, normally in concurrent programming, you think you have to wait until everything, like all the arguments of the function have come back, so to speak.
Yes.
But my point is, in this way of saying, but there is an intermediate simplification step that may mean that I've got enough arguments back. Let's say I've got a Boolean function and I'm asking for, majority or something. Then
I mean, this may already be applicable because the way parallel submit and wait work is that the result of parallel submit is a symbolic representation of that evaluation job, and these jobs are expressions, and you could actually do those kinds of expand. Or now, of course, if you multiply by 0, then that kernel is lost, right? Because you destroy the handle to that job that you are no longer interested in. So it's not that easy, I think.
what do you mean you destroy the handle? Why do you destroy the handle?
Well, I mean, if you have 0 times the result of this job and you simplify, and then you lose.
Well, but you have to know. I
Yes.
understand that, but you have to know that happened, right? You have to have
you would have to reap
after
those
simplification.
Jobs. You would have
right.
to do garbage collection on your parallel jobs.
Well, so what you would do is you would do the intermediate simplification step. Then you would look at the result and you would say, okay, now, which jobs are still being referenced here?
Yes. And instead of 0 times job equals 0, you would say 0 times job equals kill job 0, something like that. Right?
Yeah, effectively.
Mm-hmm. Yes. Or do garbage collection. Yes.
Right. But I mean, the thing I don't know is how general this phenomenon of how useful, because one of the reasons I didn't pursue this, apart from the utter nobody understood it problem with SMP, the other thing was, I had a lot of toy examples where this was relevant, but not a lot of real ones. Actually, Brian on our live stream is pointing out that you could try speculative execution on the parallel evaluation. Yeah, I mean, that's effectively what this is about. This tentative thing is effectively speculative execution. It's a good observation. Like, what would happen if I did this? And so long as these functions are pure, there's no harm in doing that. Okay, this is an interesting topic. We should explore this further. I predict there's going to be some really interesting possibilities here. And 40 years later, let's see if we can reduce out that paragraph.
Turn it into something understandable, right?
Yeah, I know. I mean, I don't think, I mean, actually that, there's a lot of training materials that were written for SMP. So I think they probably ignored this part. It's probably, they thought that was just me being crazy. Okay, somebody asked, by the way, if SMP is available. Unfortunately, no. For a long time, its source code was encrypted, but finally the encryption was, and we forgot the password. Finally, the encryption was broken by somebody much younger than the age of SMP a few years ago, and I think, let's see, I think I might. No, I probably can't do it. I don't think I can. I've got to go to a different meeting, but let's just see, just for fun, since it's so close to holiday time. Let's just see. I think that is going to give me what I want here. No. No. Oh well. I thought I might be able to. I did have a way of running it on this machine, but it's running through some kind of VAX emulator or something. Because it's written in C, but over the course of 40 years, it turns out it has enough library dependency that it really doesn't work without an emulator of the environment. But it does run, and we could try all these things. All right, we seem to have one more comment coming from the live stream. Let's just wait for that. Oh yes, I'm being given a reminder that tomorrow we are having a session about product suggestions and bugs and so on, and we'll talk about things that people bring up and what their status is. And for us, it's a really useful way to learn about people's priorities, and I hope people will tune in for that. And if you bring up outermost evaluation, we'll know you were here. And we'll also know it's not the highest priority. It's been hanging out there for 40 years, so it's probably not as urgent as other things. All right, thanks a lot. So I look forward to continuing this meeting. I'm really interested to try and. I think, as I say, this may sound unbelievably obscure, but I think there's something interesting to be gotten from it. And also, let's do it in recognition of Moses Schoenfinkel and the invention of combinators. Unfortunately, I don't know the date that combinators were invented. I tried to track that down a while ago, but the paper was submitted in 1920 by, actually, Moses Schoenfinkel was a student of David Hilbert's, and unfortunately had some kind of psychological meltdown of some sort. And I believe the paper was actually eventually submitted by Paul Bernays of other logic fame. But anyway, I have to go sort out that history if I'm going to write something about the history of combinators. Okay, good stuff. Talk to you all soon.